we continue our tour of the AFNI APQC HTML by going to the next section, which is motion-related things and outlier-related things. I realized probably what I should do is have the AFNI proc command itself open, so let me just open that as we look. So I'm going to AFNI open -e the AFNI proc command, which was up here. And just so we have this for reference as we go through this, I'm realizing that'll probably be useful. Okay, so this is the motion here. The first plot that we have displayed shows two line graphs, or two line plots over the full amount of data that we had. If you notice, the background of each one goes from white to slightly gray to white. And this shows our 3 runs and where the run breaks are, because we're simultaneously processing 3 runs of data from a single session. The top plot here is eNorm, the Euclidean norm. This is essentially our scalar parameter of how much a subject moved between a given, or at a given time point, or between a given pair of volumes. So where this is larger, there was an estimation of a larger amount of motion. The outlier fraction shows within the brain mask that we estimated. What we do is we take a look at the time series at every given ith volume, and we count the number of outliers that are appearing there in the time series at that moment. And where the fraction of outliers across the brain mask is high, we take note of that. In both cases, we have a threshold level set for censoring. So if I jump quickly to my AFNI proc command, we see that right here at these 2 lines in the command, the regress censor motion. So our eNorm, our motion parameter threshold is 0.3. And indeed, that looks about right, a little above halfway there. And then the censor outlier fraction is 0.05, which is the same as 5%. And indeed, that's where this cyan line is. And then what's being highlighted here in red is wherever either of these 2 curves is above its threshold level, that's where we see red, and that shows where there will be censoring occurring. So in this case, basically, both curves are above the threshold wherever we see red. If you see here, the red is a little bit wider in this case. It's the omnibus censoring is what's shown in red. So that's what we mean by combined censoring here. And we can also see what indices were censored because it's helpfully told to us down here. We have the AFNI style subbrick selectors, so we could take that string and use it on the command line or something if we wanted. And also we see that indeed this matches visually how much there's not a lot of censoring here. It's at 1%. Now, there are some parts that are just below threshold, and what is the correct threshold level is really still an open question in the field. I'm not even sure that that's a well-posed question that can get an answer, but these are reasonable levels to start with. Ideally, our results wouldn't depend so much on the exact threshold level that was set. Over here, we see little box plots that go along with these. BC and AC stand for before censoring and after censoring. So these are standard box plots where the box here shows the quartile, and this gray line shows the median value. So this is the 25th and 75th percentile, and then we see outliers above and below, just so you get a sense of how much motion there was for this subject. In general, the median is quite low, and even up to the 75th percentile. In the BC, you'll probably see some plots above threshold. Some of these go so high up that there must be another dot effectively up here. We don't really work to kind of display that in a different way. That these are just for average. Usually the median and interquartile range is the most useful. And then you should never see any dot above this censor line in the AC case, because after censoring, nothing should be above there. Okay. And then below is a related graph. This is just in case you need to know this level of detail. These are the 6, expand this, these are the 6 individual motion parameter estimates. the 3 translation. So DS means change of translation in the inferior superior direction, so along the z-axis, left, right, posterior, anterior. And yaw, pitch, and roll, the 3 rotations. The background coloration changes in the same way, and actually we show the censoring that was derived from these plots here. We just highlighted here just so you get a visual sense in case that helps you determine or interpret something important about individual motion here. So these red bars are not re-derived, they're just copied from above to give visual cues. You'll also see that at the boundaries between where I have runs, there will often be a large jump. That's okay. That's not really a problem. In our regression modeling, actually, if we jump back to the AFNI proc command, that's why we put regress motion per run. So what we're looking at here is the motion plot across all 3 runs concatenated. It's not actually regressed as a single motion regressor where these runs would be, these gaps at the run breaks would be problematic. And the same, so again, this may be useful to see where the most motion was in a given direction. Here we see that the pitch had a big spike here, and this is probably what's responsible for much of the censoring here. We see another little spike here in DS. At this point, note that every y-axis has its own scale range because some of these can be small and large. So this one goes from 0 to -1, and this is from 0 to 0.1 here. So just be aware of that as you're getting a visual sense of these. And the box plots, again, are here to help guide you. So this, again, is not something I look at that often. Sometimes in clinical scans, you'll see odd patterns here, essentially because there may be a pressure cuff or something that very regularly inserts something that appears like motion. Sometimes you'll see kind of a sawtooth pattern. Some of that could be related to apparent motion or other things. So looking at the individual parameters here may be useful for interpreting things. Coil heating, pillow relaxation, subject falling asleep, something like that. All right, and as we continue down here, the last thing that we'll typically show is what's called a gray plot or a carpet plot. This is something that some people really like for looking at some of the effects of motion in the data itself. So what this plot shows is the line plot here shows the scaled versions of the E-norm and the outlier fraction with the same censoring, again, just for visual reference. And there are 2 lines here. There's a blue and a green. These mirror each other so much. I think blue is, it says here, yeah, blue is the E-norm, the motion, and green is the outlier fraction with the censoring. The gray thing here, this box, is instead of looking at the time series response like we normally do with a graph as an up-down line, horizontally as time, and then we look at something going up and down like in this upper plot here, it's still time along this axis. So this is still the start of our scan and the end of it, actually the end of the 3rd run here for the session. But what we're seeing is, as we go across here, we're looking at individual time series expressing their up and down, not as a line moving up and down, but as a coloration moving either white for up or black for down. So a flat line would be just constant gray. And as you move across here and something, so for example, it's black here, this must be a relatively low value for this time series, then a relatively high value, then a mean, median value, lower, mean, things like that. And what we've done is essentially stacked all the time series, so let's say 50,000 voxels across the brain are all represented here row by row. How are they ordered? The spatial ordering within the brain doesn't matter, as it's mentioned here. This is using the PV order or the principal vector order, so they are stacked by relative similarity. If we didn't do that and we just kind of took things in some way spatially, reading line by line across the brain in 3 dimensions, it would look pretty messy and hard to see patterns. So this just basically helps accentuate patterns that where you see essentially at a given time point, is there kind of a lot of one color in or not color, one shade or gradation of shade there. So for example, across the brain here, we see it's relatively dark everywhere. So this means that there's kind of a global downward trend in the time series as they're scaled. And so yeah, each time series has been scaled. And so here there's kind of a global upward trend across a lot of them and things like that. It is not unusual to see structure in the brain. One thing I'll note here, beneath where it's red, we don't see anything, even though where there's motion, we might expect the most outliers. Actually, these time series have been censored. That's what we asked AFNI Proc to do. And censoring means that here they just have a 0 value. I should have mentioned in the beginning that what we're actually looking at is the gray plot of the residuals data sets, the error time series. This by definition has mean 0. And when we have censoring applied, the ERTS is at its mean 0 value. So this is really just 0. That's why it's this kind of middle gray. Okay, so if we didn't have censoring, we would expect this to be very bright or dark or both. Some parts of the brain go up, some parts go down when there's motion. There we go. All right, and I will pause here for that.